Hi guys, Javon here again. We'll be stopping off with rectification and be moving on to op-amp circuit theory. So by now you should know that an op-amp is an operational amplifier and it is used to amplify voltage sources. Alright, so what we're really going to tackle today is just constructing and simulating this simple circuit. So let's start by viewing what the final circuit looks like, and as you can see, op amps are driven, they are driven by two input pins inverted to one another, as you can see here, positive and negative. And today we'll be using an input at the positive terminal or the non-inverting terminal, and the input is going to be 1 volt RMS sinusoidally varying waveform. So first thing we'd like to tackle is the two types of configuration you're expected to know for op amps at this time in Form 6. So you'll need to know about the non-inverting and the inverting op amp configurations. In reality, there are a lot more than these, but in Form 6, these are the ones you'll be focusing on. So what we actually have here today is the non-inverting type, meaning that the input that we place, it will be amplified and not be inverted. So let's hook up this circuit and see how it works. So we'll start by creating a new design, and I'll just place the components on the workspace. You know how to connect them by now, so let's just place components. So the components that we'll be newly exposed to are the op amp and the voltage source, the varying. No, actually you saw the voltage varying source, so it's just the op amps you'll be newly exposed to. So we're going in the same master database, and in the grouping analog we'll be selecting analog virtual, and we are using the virtual op amp, and we'll place that ghost image on the board. So this is the only new component you need to connect. Other than this, it is just the power supplies, the DC power supplies from power sources, and the voltage source again from power sources. So let's take into consideration what is actually going to take place here. So because we are using non-inverting feedback, the loop gain, and the gain is specified by 1 plus R1 divided by R2. This gain tells us the factor by which the input would be amplified by. So we have an input of 1 volt RMS, which is roughly, let's just keep it in RMS. So we just leave it at 1 volt RMS, and the gain would be 1 plus R1 divided by R2, and R1 is 9 and R2 is 1. So we are having a gain of 1 plus 9 divided by 1, which is 1 plus 9, so we expect a gain of 10. So the voltage at the input should be amplified 10 times and displayed at the output. As you can see here, we've connected our oscilloscope, because we don't just want a voltage reading, we want a graphical representation of the waveform to see what actually occurs here. So the oscilloscope has two channels, and I didn't touch on this before, but the oscilloscope can be used to compare two waveforms by using these two channels. This is why we have the terminal B connected across the resistance R1, and A is connected at the input. So as you can see, only one of the terminals is grounded, which is A. You could have grounded B instead, because for an oscilloscope, the negative terminals are internally connected. So therefore, grounding one means you grounded the other. So let's just click play and simulate this waveform. Another thing to note are the locations of all the grounds. So ensure that you have all these ground locations before simulating the circuit, else you'll run into major issues. So we'll just bring up the oscilloscope screen as we had up earlier, and there you can see the waveform being displayed. So the trace at the bottom, the smaller sinusoidally varying one is actually the input trace, right? The taller one that is flattened at the top and bottom is actually the output waveform, and it is experiencing a phenomenon called clipping. Clipping occurs when you try to amplify the output to a greater value than the source. So we have a source of 5 volts driving our op amp. Therefore, the maximum limit we can get at the output is actually 5 volts. So even though we'd be expecting something around 10 volts, we'll actually be getting 5 volts due to clipping. So what we can do is in fact use these probes to measure the values of the channel. So let's just take a probe and drag it along here, and we should see roughly the maximum value of the sinusoidally varying voltage as well as the voltage of the clipping wave, of the clipped waveform. So let's pause this demonstration so I'll be able to just move the waveform, move the probe, sorry. And now you can see on channel A, which is reading the voltage from the source, it says 1.406 volts, which is roughly 1 volt VRMS. Because if you did your maths earlier, you'd have realized that the relationship between VRMS and the peak voltage is actually the root mean square voltage is equal to the peak voltage divided by root 2, which is roughly around 1.4, 1.3 something volts. So there we have the peak voltage, and as you can see on channel B, which represents the voltage at the output is at a level of 5.057 volts, which is approximately 5 volts, meaning clipping has occurred to the values specified by the source of this op amp. So there you have it, guys. We've demonstrated using a non-inverting op amp to amplify a sinusoidal varying voltage at the input, and also we've demonstrated clipping. In our next video, we'll be demonstrating an inverting op amp, which is basically the same principle except that the amplified output is inverted. Thanks for listening, guys. See you soon.